Module 3, Lecture B, Files and Reports. By the end of this lecture, you will be able to read measurement values from simple text files using built-in file handling, write calculated circuit and signal results to structured text reports, and use string formatting to present engineering values with units, precision, and labels. Reading measurement data. Opening data files. Opening a data file is the first step in turning stored measurements into useful engineering information. Instruments often save readings in text files, so the system must be directed to the correct accessible file before analysis can begin. This simple setup step creates the connection needed for all later data processing. When opening a measurement file, make sure you know where it is stored, what its name indicates, and how you need to access it. The file may be local, shared, or on a network drive, and its name often provides context, such as the experiment or date. Open the file for reading, not writing, to protect important measurement data from being changed or lost. When working with data files, plan for common problems such as missing files, permission issues, or disconnected drives. After a file is opened, it should be closed properly to free system resources, and modern tools can help manage this safely. Careful file handling is especially important in engineering, where repeated data processing must be reliable to support accurate measurement analysis. Python code. Opening data files. Measurement files link stored data to analysis. In this example, a small voltage file is opened, while built-in handling keeps the reading process controlled. We define a variable to store the name of the text file used for voltage readings. Keeping the file name in one place makes later file operations easier to manage and lets us change the target file path without updating multiple parts of the code. We begin by creating a small set of sample multimeter readings as text values. Each value represents a voltage measurement and can be written to a text file, similar to how real measurement data might be stored. The file is opened for writing using a context manager, so it will close properly even if an error occurs. It uses UTF-8 encoding, then writes the sample readings as separate lines by joining them with new line characters. This creates a simple text file that can be read and processed later. The program opens the voltage readings text file in read mode using UTF-8 encoding. A context manager handles the file safely by closing it automatically when finished. The program then reads every line into a list, keeping the readings in their original order. This code handles a missing measurement file without stopping the program. It catches the file not found error, uses an empty list so execution can continue, and prints a message to let the user know the file was not found. This code converts text lines from a file into numerical voltage values. It cleans each line by removing extra white space, then changes the result into a floating point number. The final output is a list of numbers ready for further analysis. The code first checks whether any voltage readings were loaded. If so, it calculates their average by adding the readings and dividing by the total count. It then prints the average to 3 decimal places, along with the opened file name and the number of readings, giving a quick summary of the processed data. The code first checks whether any voltage readings were loaded. If readings exist, displays the first measurement rounded to 2 decimal places. If none were loaded, it reports that no readings are available, so the user gets clear feedback either way. This script shows basic Python file handling by writing sample voltage readings to a text file and then reading them back. It handles the case where the file is missing by displaying an error message. When the data is available, it converts the readings to numbers, calculates the average voltage, and prints a few formatted results. Overall, it demonstrates file input and output, simple error handling, and basic data processing. Loading measurements. After a data file is opened, the program reads its text into memory and converts the values into a form suitable for analysis. It interprets each line to separate numbers, labels, units, and comments, which helps ensure the data is handled accurately for tasks such as calculations, plotting, or reporting. Measurement files are often read one line at a time because each line usually represents one record or data point. Separators such as spaces or commas show where individual values begin and end, and those text values must be converted into numbers before analysis. Once converted, the data can be used for circuit calculations such as gain or noise estimation. Measurement files are often imperfect, so file reading must account for headers, labels, units, missing values, and non-numeric entries. Handling these issues consistently helps ensure the loaded data accurately represents the experiment. Clean, reliable data is then essential for later analysis, such as signal filtering, performance calculations, and reporting. Python code. Loading measurements. Learn how to safely load simple measurement files, convert text-based readings into usable numbers, and summarize engineering data while keeping units clear. First, define the file that will store the measurement data, named voltagemeasurements.txt. Setting the file name at the start lets the code consistently write to and read from the correct location. A multi-line text string represents a small voltage measurement log. Its first two lines are comments that document the file and the units in volts, so they are ignored during processing. The remaining lines contain numeric voltage readings that will be extracted and analyzed. The text file includes one non-numeric placeholder to represent a bad data entry, followed by two valid voltage measurements, 1.198 and 1.204. This lets the script demonstrate that it can skip invalid text while correctly reading and storing the numeric values. The program opens the chosen file for writing, which creates it or replaces any existing file with the same name. A context manager ensures the file is closed properly afterward. It then writes the measurement data into the file, saving the comments and readings for later use. Set up two lists to manage the file data, one for valid voltage readings converted to numbers, and one for lines that cannot be converted. This separates usable measurements from problematic entries, making the data easier to process and analyze. The code reads a voltage measurements text file using a context manager, so the file closes automatically afterward. It processes the file line by line, tracks each line number starting at 1, and removes extra whitespace from each line to prepare the data for later use. The code skips any line that is empty or marked as a comment with a hash symbol. This prevents irrelevant or non-numeric lines from being processed, so only meaningful data is used for later analysis. The code tries to read each line as a floating point number. Valid numbers are added to the voltage data, while invalid lines are skipped and their line numbers are recorded. This keeps the measurement data numeric and makes it clear which lines were ignored. The code first checks whether any valid voltage measurements were loaded. If none were found, it raises a value error to signal that the data loading failed. This prevents the program from trying to calculate results from an empty dataset, which would cause errors later. To summarize the voltage data, first count the valid readings, then calculate the average by dividing their total by that count. Next, identify the smallest and largest readings to find the minimum and maximum voltages. Together, these values give a basic statistical overview of the measurements. The report begins with a loading measurements header, then summarizes the results of reading the voltage data. It shows how many valid samples were loaded, identifies any lines skipped because they could not be converted to numbers, and reports the average, minimum, and maximum voltages. These voltage statistics are formatted to 3 decimal places for a clear, precise overview. The script reads voltage measurements from a text file, ignoring comments and blank lines while converting valid entries into numbers. It records any lines that cannot be converted, then checks that at least one valid measurement was found. Finally, it reports the number of valid voltages, their average, minimum, and maximum, along with the lines skipped because of errors. File reading basics. An engineering text file is raw character data that must be interpreted before analysis. It may contain simple patterns, such as readings on separate lines or values separated by spaces or commas. Use built-in file handling to open, read, and close the file. Then convert the text into meaningful quantities like current or temperature before using it in calculations. Reliable file reading follows a clear sequence. Locate the file, open it in the correct mode, read and interpret its contents, convert data to numbers when needed, and close the file. Because files may include headers, timestamps, or different formats, it is important to separate descriptive text from actual data. Understanding this process helps prevent errors, such as treating a header as a number or overlooking values needed for calculations. When reading files, engineers should expect possible problems and check that the data is reliable. A file may be missing, renamed, or formatted incorrectly, and even readable data can contain strange characters or unrealistic values. Treat file reading as both data access and a quality check, so programs use valid inputs for analysis and decisions. Python code. File reading basics. Learn how to read measurement text from files, convert raw string data into usable engineering numbers, and verify the loaded values before using them. First, we set the file name for storing the measurement data. Using a clear descriptive name for the voltage log helps ensure the program reads from and writes to the intended file, keeping the code organized when handling data. The code creates a small text-based dataset containing a voltage header and 3 readings, each on its own line. This simulates data that might come from a text file, so the rest of the code can practice processing the values as if they were loaded from an external source. A text file for a voltage log is opened in write mode using UTF-8 encoding. Then a context manager handles the file safely. The program writes a header and 3 voltage readings to create a simple data log. When the block ends, the file is automatically closed, so the data is saved and resources are released. The text file, named voltagelog.txt, is opened safely in read mode using UTF-8 encoding. All of its lines are then read at once into a list of text strings, so they are ready for later processing. After reading the file, the lines include a header that is not needed for calculations. We skip the first line and keep the remaining lines as the data to process. This code converts each line of text into a floating point number. It cleans each line by removing extra white space, then changes the result into a numeric voltage reading. The final output is a list of values ready for numerical analysis. The program first checks whether any voltage readings were loaded. If the list is empty, it raises a value error to signal that no readings were found. This prevents the program from running calculations on missing data and avoids unreliable results. To summarize voltage data, calculate the average to find the typical reading, then identify the maximum and minimum values to show the highest and lowest measurements. Together, these three values give a quick view of the data's main characteristics. The code summarizes the voltage data by reporting how many measurements were read, then printing the average, minimum, and maximum values to 2 decimal places. It ends with a confirmation that the file was read successfully and the values were verified. This script shows how Python can read a simple voltage log and process its data. It creates a text file with a header and several voltage readings, then reads the file while skipping the header and converting the readings into numbers. After confirming that data was loaded, it calculates the average, minimum, and maximum voltage. It then prints these results with units and confirms that the file was read and checked successfully. Writing results. Writing text reports. Text reports turn circuit and signal calculation results into permanent records that can be reviewed, shared, and archived. They capture key values such as voltage, current, and power, making them useful for lab work, design checks, and troubleshooting. Because they are easy to access across systems, they are a basic tool for automated engineering documentation. A clear technical report should explain results, not just present data. Label what each result means and include essential context, such as the circuit being measured or the source and sampling rate in signal analysis. Clear reporting helps prevent misunderstandings that could affect design, safety, and technical accuracy. A text report should be a concise technical document with a clear beginning, middle, and end. It should state the purpose and analysis type, present organized results with clear labels, and finish with a brief summary or interpretation, such as whether values meet limits. This structure helps make results easy to understand in labs, monitoring systems, and other technical settings without rerunning the analysis. Python code. Writing text reports. This script creates a short engineering report, formats circuit values with readable units, and previews the saved text file. The circuit is defined using 3 key values: a 12-volt source, a 470 ohm resistance, and a component power rating of 0.25 watts. These inputs provide the basis for later calculations of the circuit's behavior. The code finds the circuit current by dividing the source voltage by the resistance, then calculates the resistor's power by multiplying voltage by current. It reports this power in watts and also converts it to milliwatts by multiplying by 1000 for easier reading. Begin by choosing a clear report file name, such as circuitreport.txt, so its purpose is easy to recognize. Then create an empty collection for the report lines, which lets you build the report one line at a time before saving it to the file. The code starts building a circuit calculation report by adding a clear title and a separator for readability. It then records the source voltage, formatted to 2 decimal places and labeled in volts, so the value is easy to read and understand. The code builds a readable report by adding labeled engineering results to a list. It formats resistance in ohms, converts current to milliamps, and converts power to milliwatts, using appropriate decimal precision for each value. The code compares the calculated power with the component's watt rating to judge whether the circuit is operating safely. If the power is within the rating, it reports that the component is within its limit. If not, it reports that the rating has been exceeded. To complete the report, add a line showing the power rating status using the status text already determined. Then add an end of report line and combine all report lines into one text block separated by new lines. The final result is ready to be saved to a file or used for further processing. The code opens a report file for writing with UTF-8 encoding, then writes the report text into it. It stores the number of characters written, and the context manager makes sure the file is closed properly, even if an error occurs. Open the report file for reading with UTF-8 encoding so special characters are handled correctly. Then, read the full file into memory to check that the report was saved properly and make its contents available for later display or use. The code confirms that the report was saved by showing how many characters were written and naming the file. It then displays the saved report in the console, so you can quickly verify its contents and see that the file was written correctly. This script creates a basic circuit report by using the source voltage and resistance to calculate current and power. It compares the power to the component's rating to decide whether the circuit is operating safely. The report summarizes the key values in readable units, saves them to a text file, then reads the file back to confirm the saved content and print a short preview. Structured text reports. A structured text report organizes calculated results so others can understand and review them later. In circuit and signal work, it should preserve context by clearly identifying the report and separating measurements, calculations, and conclusions. This structure supports good engineering practice by making results easier to interpret, troubleshoot, and document. When reports need to be useful beyond a single session, a clear structure is essential. Consistent labels and formats help others quickly understand measurements, compare results, and archive information. This turns a report from a temporary note into a dependable tool for communication and quality control. A clear report separates raw data from interpretation and guides the reader from purpose to conclusion. It should state the goal, note key assumptions or settings, label the main results, and end with a brief summary. This structure makes calculations easier to repeat, compare, share, and review, which is essential for trustworthy professional documentation. Python code. Structured text reports. Structured reports help preserve the context of engineering calculations, making results easier to understand and verify. Clear labels and units reduce the chance of misreading values, and the goal is to produce one concise, well-organized report. The setup records voltage measurements at specific time points so that change in voltage over time can be analyzed. It also defines a fixed resistance value, which is used later to calculate electrical quantities such as current and power from the measured data. The code first verifies that the time measurements and voltage measurements have the same length, so every time point is paired with a voltage value. If they do not match, it raises an error to stop the process. This check prevents later calculations from using mismatched data. Find the peak voltage by identifying the highest value in the voltage measurements, and find the average voltage by taking the mean of all measurements. Then, use Ohm's law to determine the peak current by dividing the peak voltage by the resistance. Peak power is found by squaring the peak voltage and dividing by the resistance. The peak voltage is then checked against a 3.3 volt limit. If it is within that limit, the result passes. If it exceeds the limit, it fails. The report is built as a series of text lines for a voltage signal test. It begins with a clear title and a separator, then states that the test checks a resistor load signal. It also includes the load resistance in ohms, using the stored resistance value to keep the report accurate and consistent. The report adds a clear input measurement section to summarize the collected data. It includes the number of voltage samples by counting the voltage entries, then reports the measurement time range using the first and last time values rounded to 2 decimal places. This gives a concise overview of the input data with appropriate units. The report adds a separated section for calculated results, then records the peak and average voltage values. Each voltage is formatted to 2 decimal places, giving a clear and concise summary of the key measurement results. The report adds a concise summary of the circuit results and a final conclusion. It converts peak current from amperes to milliamperes and peak power from watts to milliwatts, with both values shown to 2 decimal places. It also checks whether the peak voltage stays within the limit and reports the result as pass or fail. The code saves a report to a chosen file by opening it in write mode with UTF-8 encoding. It writes the report lines as a structured text file, separating each line with a new line. Using the with open approach also ensures the file is closed properly when writing is finished. The code opens a text report for reading with UTF-8 encoding, then reads its contents as lines. It keeps only the first 12 lines to create a short preview, which avoids processing more of the file than needed. The code prints a short preview of the structured report. It first labels the preview, then displays the first 12 lines that were already read from the file. This gives a quick view of the report without opening the full file. This script creates a concise voltage test report from time-based measurements. It first confirms the time and voltage data match, then calculates peak and average voltage along with peak current and power using a fixed resistance. It checks whether the peak voltage stays within the allowed limit and marks the test as pass or fail. The script saves the report and prints a short preview of the results. Formatting report values. Well-formatted reports turn raw numbers into meaningful engineering information by adding clear labels, units, and context. In circuit and signal work, the same value can represent different quantities, so formatting helps prevent ambiguity. Stating results with appropriate units, such as a cutoff frequency in kilohertz or power dissipation in watts, makes calculations easier to understand, use, and trace later. When reporting measured values, show only the digits justified by the data's precision. Too few digits can hide useful information, while too many can imply accuracy the instrument cannot support. Use sensible rounding, such as reporting a filter gain as 0.707 rather than an unnecessarily long decimal. And keep formatting consistent, so values like voltage and frequency are easy to compare. In engineering reports, units and labels are essential for clear and reliable communication. Values should always be reported with the correct units, especially when scales change, such as volts to millivolts. Using appropriate prefixes like microseconds or millivolts makes results easier to read and helps prevent mistakes in engineering decisions. Python code. Formatting report values. Calculated engineering values should be presented clearly with labels and units to avoid ambiguity. Use an appropriate level of precision to show realistic confidence in the measurement. The script stores key circuit and signal values for later calculations and reporting. These include a cutoff frequency of 1247.83 Hz, resistor power of 0.18364 watts, peak-to-peak voltage of 3.297 volts, and a rise time of 0.0000472 seconds. These unit conversions make engineering values easier to read and interpret. Cutoff frequency is converted from hertz to kilohertz by dividing by 1000, power from watts to milliwatts by multiplying by 1000, and rise time from seconds to microseconds by multiplying by 1 million. These changes express large, small, or very short measurements in more practical units. The report is built by collecting formatted lines of text, starting with the title, Electrical Test Report. It then adds key results, such as cutoff frequency in kilohertz and resistor power in milliwatts. Each value is formatted with controlled decimal precision and alignment, so the final report is consistent, neat, and easy to read. The report is expanded with key voltage and timing details. It adds the peak-to-peak voltage and rise time, both shown to 2 decimal places with consistent alignment. A final status line notes that the values were rounded to make the report clearer and easier to read. The code combines a list of report lines into one formatted text block by joining them with new line characters. This puts each report line on its own line, making the final string clear, organized, and ready to print or save. The code displays the formatted report in the console so you can immediately check the results. This makes it easy to verify that the calculated values are clear, readable, and ready to communicate as engineering data. The code defines a report file name and stores it in a separate variable for later use when saving the report. Keeping the file name separate makes the code easier to update if the output file name changes. The program opens the report file for writing, creating it, or replacing an existing version. A context manager ensures the file is closed safely after use. It then writes the report text into the file so the formatted report can be saved and shared later. The code displays a confirmation message in the console after saving the report. It uses the print function to show that the report file was saved and includes the file name, so the user knows where to find it. The script takes key circuit test measurements such as cutoff frequency, power, voltage, and rise time, and converts them into readable engineering units. It then creates a clear, rounded report with units included, prints it for immediate review, and saves it as a text file. This provides both quick visibility and a stored record of the formatted results. Formatted engineering reports. Frequency formatting. Engineering reports should format frequency values with clear units and appropriate scale, because frequencies can range from tiny fractions of a hertz to billions of hertz. Writing 1 megahertz instead of 1 million hertz makes the value easier to read, compare, and interpret. This clarity is especially important in circuit and signal reports, where frequency often describes key behavior, such as filtering or sampling. Frequency values should be formatted to balance precision with readability. Too many decimals can make reports cluttered and imply more accuracy than is justified, while too few can hide important differences near key frequencies. For example, a filter cutoff may be clearer as 1.25 kHz rather than a long value in hertz, but precision oscillators may require more digits. The goal is to present numerical evidence in a way that supports clear interpretation and decision-making. Use frequency units consistently so reports are easy to read and verify. Choose units that fit the domain, such as hertz or kilohertz for audio, and megahertz or gigahertz for wireless or high-speed digital systems. Clear labels and consistent formatting reduce confusion and help readers compare values without extra mental conversion. Python code, frequency formatting. When reporting frequencies in engineering work, format them for quick readability. Use appropriate prefixes, sensible precision, and clear unit labels so the values are easy to understand. Keep the presentation concise, especially in lecture materials. We create a list of sample frequency measurements in Hertz, ranging from very small to very large values. This gives us data to later show how frequencies can be displayed in more readable units, such as kilohertz or gigahertz, based on their size. A set of frequency scale pairs links powers of 10 to standard units: gigahertz, megahertz, kilohertz, and hertz. By comparing a frequency value with these scale factors, the value can be displayed in the most suitable unit, making engineering reports clearer and more consistent. The function converts a frequency in hertz into the largest suitable unit by comparing its absolute value against available scale factors. When it finds a matching scale, it divides the frequency by that factor and returns a human-readable value rounded to 2 decimal places with the correct unit label. When a frequency does not fit larger units such as gigahertz, megahertz, or kilohertz, the function reports it in hertz. It keeps the value to 2 decimal places and aligns it consistently, making smaller frequency values clear and readable in the report. We create a list to store the text for a formatted engineering report. It begins with a report title and a frequency results section header, giving the output a clear structure before the formatted measurement data is added. The process loops through each frequency and uses its position in the list to label it in the report. Each value is converted into a readable unit, such as hertz, kilohertz, or megahertz, then combined with its label. The final result is a clear report where every frequency point is formatted and identified. The code combines formatted report lines into one multi-line text block using the join method with new line separators. This creates a clear engineering report that is ready to print or display. The code prints the final engineering report to the console. It outputs a single text block created by combining the formatted frequency lines, giving the user a compact and readable summary of the frequency measurements. This script turns frequency measurements in hertz into clearer engineering units, such as gigahertz, megahertz, kilohertz, or hertz. For each value, it chooses the largest suitable unit, scales the number, and formats it to 2 decimal places with the correct label. It then prints a compact report with neatly aligned, easy-to-read frequency values for engineering use. Units in reports. In engineering reports, every number should include its unit, so the meaning is clear. A value without a unit can be ambiguous, especially in circuit and signal work where volts, amperes, and other quantities mean very different things. Showing the unit with the value makes reports easier to understand, share, and review later without returning to the original program. Always include units in engineering reports to keep data clear and consistent as it moves between tools and people. Unit labels prevent mistakes, such as confusing hertz with kilohertz or treating 44.1 as meaningful without context. Clear units support troubleshooting, design reviews, and safe, reasonable analysis. Choose units that match the scale, purpose, and audience of your report. Engineering prefixes can make very large or small values easier to read, such as using microamperes or milliseconds instead of awkward decimals. Use spelled-out units when helpful for beginners, standard symbols for expert audiences, and keep formatting consistent so readers can compare values clearly. Python code, units in reports. Engineering reports should present values with clear units and pair every number with its label. Choosing appropriate units makes results easier to read and understand. Using Ohm's law, resistance is found by dividing voltage by current. With a voltage of 5.0 volts and a current of 0.002 amperes, this calculates the circuit's resistance, which represents how much it opposes the flow of current. Convert values into common engineering units for easier reading. Current from amperes to milliamperes, resistance from ohms to kiloohms, and power from watts to milliwatts. Power is found by multiplying voltage by current, then scaling the result to milliwatts. These conversions make the final values easier to report and compare. The report is set up by creating an empty list to store its formatted lines. A clear title is added first, followed by a dash separator to make the output easier to read. These steps establish the basic structure before adding the engineering details. The report is built by adding formatted lines for voltage, current, resistance, and power. Each value is converted to an appropriate unit when needed, such as milliamps, kiloohms, or milliwatts, and displayed with 2 decimal places. This keeps the measurements clear, consistent, and easy to read. The sampling rate is set to 44.1 kHz, a common audio rate. It is converted from hertz to kilohertz for readability, then added to the report with 1 decimal place so the result is clear and easy to understand. The report lines are combined into one complete text block, with line breaks preserved between them. That text is then saved in a UTF-8 encoded file named Engineering Report, so special characters are handled correctly. This creates a shareable text version of the formatted engineering report. To inspect the saved report, the file is opened in read mode using UTF-8 encoding, so its text is interpreted correctly. A context manager handles the file safely and closes it automatically when reading is complete. The full report content is then stored for later display or processing. The code prints the saved report text to the console, so you can review the formatted engineering report. This lets you check that the values and units from the previously loaded file are displayed correctly. This script creates a concise engineering report from basic electrical values. It uses voltage and current to calculate resistance and power, then converts the results into readable units such as milliamps, kiloohms, milliwatts, and kilohertz. The formatted report is saved to a text file, read back, and printed, showing each value with clear labels, units, and appropriate precision. Aligned units. Engineering reports are easier to read when labels, values, and units are aligned consistently. This is especially important in circuit and signal work, where many measurements may need to be compared quickly. A predictable layout helps readers spot patterns, differences, and possible errors, while reducing the chance of misreading during analysis or troubleshooting. Aligned units make technical reports clearer and more professional. Give labels, values, and units enough consistent space so similar items line up across rows, especially when values have different lengths or precision. This makes comparisons easier to read and helps turn raw measurements into a clear technical summary. Aligning units in engineering reports makes the information easier to read, compare, and trust. Consistent formatting helps readers spot unusual values or incorrect ranges and supports clearer analysis across tests. With careful formatting, raw data becomes a useful, reliable report rather than just a record of results. Python code, aligned units. Use built-in Python to format engineering reports, so labels, values, and units line up in consistent columns. This makes the output easier to read and compare without needing extra libraries. A list of measurements stores circuit or signal data as tuples. Each tuple contains a label, a numeric value, and a unit, such as an input voltage in volts or a sensor current in amperes. This structure keeps the data organized so it can be processed and formatted easily later. This data stores 3 circuit measurements as labeled entries: a load resistance of 220 ohms, a cutoff frequency of 1450 Hz, and a cable length of 36 inches. Each entry includes a label, value, and unit, making the measurements easy to format in a report. The process builds a formatted report one line at a time. It starts with an empty list, then goes through each measurement, using its label, value, and unit to create a neatly aligned line. Each value is shown to 3 decimal places, so the final report has consistent columns and is easy to read. The report text is built by adding a clear header to the formatted measurement lines. It is then saved as a UTF-8 encoded text file, creating an aligned engineering report that can be stored, shared, or reviewed later. The code displays the formatted engineering report in the console, so you can quickly review its layout and content. This helps confirm that labels, values, and units are aligned and formatted correctly before the report is used elsewhere. This script creates a neatly aligned engineering report from a list of measurements. Each label, numeric value, and unit is formatted into columns, with values shown to 3 decimal places. The completed report is saved to a text file and also printed to the console, so you can inspect the aligned output. In this lecture, you learn to read measurement values from simple text files using built-in file handling, write calculated circuit and signal results to structured text reports, and use string formatting to present engineering values with units, precision, and labels. In the next module, Module 4, we will go over none. Thank you for your attention. See you all in the next lecture.